We're starting a new chapter with section 14.1, and the entire chapter 14 has to do with chemical kinetics. And some of the things that we are going to explore in chemical kinetics is, or are, how fast chemical reactions can go and what factors affect how fast chemical reactions can go. Section 14.1 deals with rate of reactions, so we are just, for now, just understand how we define the speed of a reaction. Okay, so we use the term rate of a chemical reaction, or more specifically, reaction rate, to refer to the change in concentration of a given product or a given reactant over time for a given chemical reaction. We can measure that as the disappearance of a reactant or as the appearance of a product. It doesn't really matter which one you pick, where you are going to obtain the same result, because you want to refer to the overall chemical reaction, how fast the overall chemical reaction can go. And it depends on whether you're measuring reactants or products, but the result should be the same. To express how fast these chemical reactions are, you usually use units of molarity per unit time. But if you want to have a broader view of what's going on here, you are basically following how the amount of matter is changing over time. Okay, amount of matter per unit time. The change in the amount of matter per unit time, defined as the disappearance of a reactant or the appearance of a product. Factors that affect these reaction rates. You have the nature of the reactants. Sometimes the best explanation for that is because they behave that way. Okay, particle size. That goes for solid reactants, and that has to do with the surface area. Basically, if you have an increased surface area, you have more of the material exposed to the reaction, and therefore they will proceed at a faster rate. So you are consuming a larger number of particles per unit time because there are more particles exposed to the environment, if you will. Concentration of reactants. Usually the impact of the concentration of reactants is, well, if you have more, then the reaction goes faster. Okay. Temperature. The reaction happens because these molecules come into contact. The more energy they have, the more successful that contact will be, and that's why temperature usually increases the rate of a reaction. Catalysts also tend to increase the speed of reactions because they introduce some other ways in which they can, the reactants can interact with each other. Sometimes they lower the energy required to proceed in that reaction, and sometimes they provide alternative mechanisms for that reaction to occur. For chapter 14 purposes, we are going to focus our attention on concentration, temperature, and catalysts. Okay, we are not going to deal too much with the nature of the reactants or particle size. Probably chapter 19, we are going to understand a little better the nature of the reactants. But for now, just concentration, temperature, and catalyst. So how do we measure these reaction rates? Well, you need to determine the amount of matter at different time intervals so that you can express how fast this reaction can go, right? So you express that as a change in concentration. It could be for the reactant, could be for the product. It doesn't really matter. The reaction rate is going to be the same whether you pick the product or the reactant. One thing that you need to keep in mind is that we are expressing this as a change in concentration over time. For a reactant, the change in concentration is negative because the concentration is becoming smaller and smaller and smaller. And for a product, the change in concentration is positive because the concentration is increasing over time. What does that have anything to do with anything? Well, because you have a reactant here and the reactant is disappearing, then you add a negative sign here. That is a reflection that the concentration of the reactant is decreasing. You need to add that a negative sign there. Let's put it this way: if you are if you're measuring the change in concentration but measuring the final concentration and subtracting the initial concentration, because it's a reactant, you're gonna have that the final concentration is smaller, so the difference is gonna be negative, and therefore you have to multiply by a negative sign here on front, so that the rate of reaction that you are determining is positive. And let's say it's always positive. You express the rate of a reaction as always positive, and understand that the distinction here is that you in this case you are referring to the rate of the reaction. With these terms over here, you are referring to either the disappearance of a reactant or the appearance of a product, and those are related with the overall rate of reaction. Again, the units usually are measured in terms of molarity per unit time, so frequently it's molar per second. You can also express the per second as seconds to the -1. Okay, if the reaction is a little bit slower, then you can change the unit to something that is more manageable. You can refer to molar per minute or molar per hour. It depends just on how fast the reaction is. You can adapt those units to whatever you need. So if you are expressing these reaction rates, then you should be able to measure the concentrations. Okay, and again, you can measure the concentration of a reactant. Okay, measure reactants or measure products. It doesn't really matter, because after all they are all connected through the chemical reaction. So if you can establish a stoichiometric relationship between reactants and products, you can do the same with the reaction rates for each one of those. Okay, there are several techniques that you can use to follow or to measure these concentrations. One of the most used is colorimetry. Let's call it colorimetry, in which either your reactant or your product produce a color when they are dissolved in water. Is that a requirement? Can you only follow reactants or products that are colorful? Not really, but it's just one of the easiest way to do it. Okay, so you just adapt your technique to whatever you can do with those reactants. So this is one of the easiest one. And here, color intensity increases if the molarity increases. Okay, so and you can determine that you can prepare different solutions at different concentrations and prepare a calibration curve, which is what you have here. Then you can relate that color with the concentration that you have, and it could be again a reactant or a product. If any of those produce a colorful solution, you can follow it by colorimetry. So the bottom line here is that you should be able to measure the concentration of at least one substance in that reaction so that you can calculate the reaction rate for it. So to understand better what's going on here, we have our generic reaction. It's just one reactant going to one product, and this is expressing change in concentration, changing the molarity over time. Okay, therefore the one that is decreasing the concentration, that's A, that's your reactant. The one that is increasing the concentration, that's B, your product. Okay, and how do we use these rates here, those changes? So let's assume for now, let's focus our attention on T equal 0 and T2 equal 40. Okay, this is seconds, so at 40 seconds, okay, at 40 seconds, the concentration of A is approximately 0.20, and the concentration of B is approximately 0.8. What was at time 0? At 0 seconds, the concentration of A was 1.0, and the concentration of B was 0. So what is delta A? Delta A is your final concentration, 0.20, minus your initial, that would be 1. and this is equal 0.2 minus 1, this is minus 0.80, and the change in concentration for B is equal 0.80 minus 0 equals 0.80. So since the stoichiometry of this reaction is 1 to 1, basically if you consume 1 mole of A, you will produce 1 mole of B. In this case, you consume 0.80 moles of A, you produced 0.80 moles of B. Now that is the change in concentration. What is the change in the rate, so to speak? So here delta T is equal 40 minus 0 equal 40. So this first term here minus delta A over delta T is equal to minus 80 over 40. No, 0.40. 40. So these negative signs cancel, and this is approximately 0.020 molar per second. That is the reaction rate for this reaction based on the information that you can obtain from the graph. So your reaction rate is equal 0.020 molar per second. And it doesn't matter whether you use A or B to calculate it, the reaction rate is going to be the same regardless of the species that you picked to express the reaction rate. Okay? Now, what does stoichiometry have anything to do with reaction rates? Well, you can pick any substance participating in the reaction to express the reaction rate. And it doesn't matter which one you pick, you should obtain the same value. So to do so, and to respect what the stoichiometry of the reaction is, well, you have that the change in concentration of A is going to be equal to plus the change in concentration of B, and that's minus. And when it comes to C, then it's 1/2. And why do you use 1/2? Because you are kind of normalizing what's going on with the reaction. You want kind of a constant number of moles per unit time to express the rate of the reaction. So if 1 mole of A disappears, let's put it this way. If 1 mole of A disappears, then 2 moles of C appear. So you want to have the same number regardless of what species you are using. That's why you divide by 2. Okay, basically you are using the stoichiometric factor from the reaction to divide the change in concentration over time for that particular substance. So now we have this case. All right, and let's again use 40 seconds. So we already know that delta T is equal 40 seconds from 0 to 40. Now at 40, the concentration of A is equal 0.40. The concentration of B is equal 0.60, and the concentration of C is equal to 1.2. Okay? At T equals 0, A is equal to 1, B is equal to 0, and C is equal to 0. Therefore, minus delta A over delta T is equal to minus, here we have 0.40 minus 1 divided by 40. Okay, and this is minus 0.60 over 40. And this is going to be equal to 0.15 molar per second. Now, what if we pick C, for example? 1/2 delta C over delta T is going to be equal to plus 1.2, sorry, plus 1/2 1.2 over 40, which is pretty much 0.6 divided by 40, and it's 0.015 molar per second. So it doesn't really matter which one you pick, you are obtaining the same rate. So you just have to pick one, and if you are following the reaction, you just have to follow one of the substances participating in the reaction, and you can obtain your rate of reaction. Okay? So in general, for any given reaction, what you are doing is basically taking the stoichiometric coefficient in each one of these substances, and you are dividing by that. Okay, so that you are normalizing your reaction rate so that you can express, you will have the same reaction rate regardless of what substance you are using to define your reaction rate. Things to remember here: any any reactant, you have to add a negative sign, and here I'm just overemphasizing the product's positive sign. Okay, products are positive, and reactants are negative. And the reason for the negative sign, remember one more time, is because the reactants are disappearing. Now, for this reaction, we have 2A equal B. Express the reaction rate as an equation in terms of the rate of change of A and the rate of change of B. So rate is going to be equal to, if it's A and it's a reactant, number one, you have a negative sign. You have a stoichiometric coefficient of 2, so you have to divide by 2, so you have 1/2 here, and the rest is normal. We have delta A over delta T, and this has to be equal to B, and B is plus delta B over delta T. And you may be asking, what happened with the stoichiometric coefficient of B? Well, with B, technically you are using 1/1, which is 1, so that's why you don't include it there. So you can omit it. Now, this is the next question is kind of important. Well, expressing words. Let's skip that one. What I want to say is that, what if you want to express the reaction rate of one particular substance in terms of the other one? So let's say that we are following B, and then you want to know what is the rate of disappearance of A, for example. And keep in mind this: when you are looking at this, that's the rate of disappearance of A. Okay, the whole thing is the reaction rate, but that just that term delta A over delta T, that's the rate of disappearance of A. Okay, so but what I wanted to do here is that if I wanted to express the rate of disappearance of A in terms of B, then all you have to do is, let's rewrite that. So we have 1/2 delta A over delta T, and this is equal to plus delta B over delta T. Let's assume that what you are doing is you are following B, so you can determine the rate of appearance of B, but you want to know what is the rate of A. You cannot follow A, you cannot determine the concentration of A, you cannot produce the pretty graph that we had before. So what did you do? Well, you take this as an equation, and you solve for delta A over delta T, which means delta A is going to be delta A over delta T is equal to minus 2 delta B over delta T. Okay, So in other words, you can say that the rate of disappearance of delta of A is equal to twice the rate of appearance of B, pretty much. Now here we have a nice exercise. We have the rate of a reaction and we want to understand what is the reaction. Okay, where do we start? So we have three components in this reaction. You have X, Y, and Z. And you might be thinking, well, X plus Y equals Z. Well, not so much. Why? Because you have here, well, there is none here, but you already know that this is 1 over 1, right? Now let me erase that. So that is related to what is the stoichiometric coefficient for each one of these species. Now the other thing that you have to keep in mind is that there is a negative sign here and there is a negative sign there. So X and Z are reactants. So it's not X plus Y, it's X plus Z that goes to Y. But we are not done yet because we have those stoichiometric coefficients there. So we need to put a 2 in front of X. This implies that it's 1, so Z is okay. And then we have to take a 3 and put it in front of Y. So 2X plus Z goes to 3Y. So that is your reaction. Okay? And based on that reaction, this is what you would expect here. This is Y, the yellow is X, and Z is the green one. Okay, and it's up to you if you want to determine what the rate is. You can do it from the graph if you want to. You don't have to, but you're welcome to do so. So let's work with these numbers. We have the rate of appearance of ammonia according to the following reaction, which we have here. And the rate of appearance of ammonia, okay, is 0.0245 molar per second. Okay. Number one, what is the rate of reaction? And rate, I will ask you to always do this exercise, even if I'm giving you only the rate for ammonia. Always write everything. Okay, so for example, here the rate is going to be minus, stoichiometric coefficient is 1, so we can omit it, delta concentration of nitrogen over time, it's equal to minus 1/3, because you have a 3 in front of the hydrogen, delta concentration of hydrogen over time, and that has to be equal to plus 1/2 delta concentration of ammonia over time. Now the term that we have is this one. Okay, this value that you have here, that is just that. That doesn't include the half that you have there. Therefore, rate is equal to plus 1/2 of 0.0245. Okay. And this is equal to 0.0225. I think we can cut it here on the 5. So that is the reaction rate. This is the rate of appearance of ammonia, but this is your reaction rate. Now the other question is, what is the rate of hydrogen? So what we are asking is, what is this term here by itself? So you have two different ways to do this. Okay, you can, let's put it this way, you can focus on these two and take it from there, or you can use the reaction rate that you already calculated and relate it with the concentration of hydrogen. Okay, so that means rate is equal to minus 1/3 the rate of hydrogen over time, which means that the rate of hydrogen is equal to minus 3 times the rate. So this is equal to minus 3 times 0.0123, which is equal to minus 0.0369 molar second. Okay, now one thing that at some point that's going to be confusing is we are referring to the rate of disappearance. Whenever we say rate of disappearance, we are implying the positive sign. Okay, so this is the value of delta H. This is delta concentration over time. But the rate of disappearance is equal to 0.0369. Okay, difference here, if we were saying what is the rate of hydrogen, we are not referring that to a disappearance or not, then okay, you report minus 0.0369. That implies that this is the disappearance because it's negative. So in short, reaction rates will be affected by 5 factors: the nature of reactants, particle size, concentration of reactant, temperature, and presence of a catalyst. We are going to focus our attention mostly on concentration, temperature, and presence catalyst. Okay, and the reaction rate can be measured as the disappearance of a reactant or the appearance of a product. We have that for a product you use plus 1 over x, delta x over delta t, and for a reactant you have to add a negative sign. Okay, here stoichiometry matters. You have to take it into consideration because you have fractions there that depend on the stoichiometry of the reaction. Okay.